Assalamualaikum and hello everyone. So we are going to present our group project for CSC 787 Advanced Data Organization subject title Data Modeling for Postgraduate Academic System. So this is our team members. Our team consists of three members, which is first me, Nurin Izzah binti Zain Abidin, and second is Nur Khairuna binti Muhammad Kamal, and third is Khairunisa binti Zaid Azmi. So we will begin by introducing the core foundation of our project, which is the postgraduate academic data model. So a data model plays a crucial role in providing structure and consistency for managing educational data. It ensures that student records, course data, and assessment results are systematically stored, tracked, and retrieved. So this system is not just about storing data, it supports broader functions such as academic planning, performance reporting, and the future development of educational system. So our key objectives are threefold, which is first to develop a conceptual and implementable data model for reflects real academic workflows. Second, to stimulate actual system operations, and third, to facilitate data integrity visualization and analysis, ultimately supporting better academic decision making. Let's now look at the scope of our project, which outlines that what this system covers and what it is designed to achieve. So, under entities covered, we have model core academic components such as students, lecturers, programs, and courses, as well as more specific academic operations like course enrollments, research projects, thesis submissions, publication, conferences, exams, and student fees. So, the process covered span the typical postgraduate life cycle, including enrollment, supervision, assessment, and financial tracking. And in terms of system functionality, our implementation allows an interactive data viewing interface, which is a basic AR visualization, and built-in flexibility for future extensibility, such as integration with academic dashboards or database systems. So this broad scope ensures our model is not only conceptually strong, but practically applicable for real-world academic system. Here, we present the key entities in our model. Starting with the student entity, this table captures all essential student profile details. So student ID is the primary key, which is a unique identifier for each student. Additional attributes like full name, date of birth, gender, and phone captures personal demographics. Address, city, state, and nationality provide location details for administrative purpose. Intake semester helps track when the student begin their studies, while program ID is a foreign key that links each student to their respective academic program. The status field shows whether the student is currently active, completed, or has withdrawn from the program. Moving on to the lecturer entity, each lecturer is uniquely identified by lecturer ID, which serves as the primary key. So we include contact fields like full name, email, and phone. Academic alignment is captured through department and faculty, while expertise area and position provide further context about their qualifications and role in the institution. Then we have the program entity, defined by program ID as its primary key. It includes the program name, associated department and faculty, total number of semester, and the program level, whether master or PhD. The mode field specifies whether it's a coursework, research, or mixed mode program. The course entity includes attributes such as course ID, course name, a brief description, credit hour, and the semester offered. And it linked back to the program through program ID as a foreign key, ensuring each course is tied to a valid academic program. And other than that, we have the course enrollment entity, which serves as a bridge between students and the courses they are registered for. The primary key is enrollment ID. Foreign key, student ID, and course ID form the many-to-many relationship between students and course. And semester indicates when the course was taken, and grade records for final result. Next, continue with our entity modeling, which is the research project entity. Each project is identified by project ID with student ID and supervisor ID, serving as foreign keys linking the project to the student and their supervising lecturer. Title, start date, and end date document the scope and timeline of the research. The status field tracks whether the project is ongoing, completed, or withdrawn, while research type distinguish whether the study is qualitative, quantitative, or mixed method. Following that, the thesis submission entity tracks the submission and evaluation process. Thesis ID is the primary key, while student ID and project ID link the thesis to the student and the original research project. Submission date, defense date, and submission type help log the progression from proposal to final defense. The examiner ID points to the lecturer evaluating the work, and the grade and status fields document the outcome and review stage. So next is the publication entity. Each publication is uniquely tracked using publication ID. The table links to both the student ID and supervisor ID to identify the authorship and academic support involved. Core attributes like title, journal name, date published, and DOI record publication metadata, while the indexing field identifies whether the journal is indexed in Scopus or Web of Science. Lastly, the conference entity logs academic conference participation. Conference ID is the primary key while student ID acts as the foreign key. The name and location indicate where the event took place while date captures when it occurred. Paper title and type specify what was presented and whether the event was national or international. Next, let's look into the key entities and attributes that support the academic life cycle, which is exam and student fee. Each exam record is uniquely identified using exam ID, and which is the primary key. It connects to both the student and course entities through foreign key, which is student ID, and course ID, which is allowing us to track which student set for which course exam. The inclusion of exam date, exam time, and duration supports effective exam planning and logistics. Attributes like venue, semester, and academic year provide important contextual information, ensure we can manage where exams are held each session. So next we have the student fee entity, which manage the financial dimension of students' academic journey. This table is anchored by fee ID as the primary key and link back to the student table via the student ID foreign key. The study mode field helps differentiate full-time and part-time enrollments, while semester provide the time reference for the billing cycle. So to track financial progress, we include total fee paid, balance, and payment date. And finally, the fee status and payment method fields provide insight into the student's payment condition and how the transaction was processed. Moving on, we are going to look at the core relationships between the main entities in our postgraduate educational data model. We can see here from row 1 and 2 highlight the program student and program course relationship. Each program can have many students, but a student belongs to only one program. Similarly, each program can offer multiple courses, but each course is tied to a specific program. Row 3 and Row 4 involve course enrollments, which we can see students can enroll in multiple courses. Each enrollment record is unique to a specific course and student pairing. Row 5 and 6 shows that the academic research aspect, where a lecturer can supervise many research projects. Each student may have one or more research projects depending on the institution's rule. Row 7 to 9 focus on thesis and supervision. Each research project results in one thesis submission. A student may have multiple submissions like draft and final versions. A lecturer can act as examiners or for these submissions. So row 10 and 11 cover publications where students may publish many papers. Lecturer can be involved as co-authors or supervisors. Row 12 address conference participation, where students are allowed to attend multiple conferences to share their work. Row 13 and 14 deal with exams, where each course may have more than one exam per semester. Students also take multiple exams as part of their academic evaluation. Row 15 adds a financial element where students may have multiple fee transactions every semester. And from here, overall, we can see this data model captures the complex academic life cycle of a postgraduate student, from enrollment to coursework, research, thesis submission, publications, and financial obligations.
Next, let me walk you through the conceptual entity relationship diagram for our postgraduate education data management system. At the center of our model is the student entity. Each student record includes details such as name, contact information, date of birth, nationality, and is linked to a specific academic program through the program ID. Moving right, the program entity defines each postgraduate program. Each program can have multiple students and courses, establishing a one-to-many relationship. The course entity details every course offered within a program, including course name, description, credit hours, and the semester it is offered. Students enroll in these courses, and this relationship is managed through the course enrollment entity, which records which student took which course in which semester and what grade they received. For academic assessment, the exam entity track each exam a student takes for a particular course, including the date, time duration, venue, and academic year. On the left side, we see entities related to research and scholarly activities. The research project entity links each student to their research project supervised by a lecturer. Each research project can lead to a thesis submission, which record the detail of the thesis, its examiner submission, and defense dates and status. The lecturer entity represent academic staff, including their expertise and contact detail. Lecturers supervise research project and may also act as examiners for thesis submission. Scholarly output is captured in the publication entity, which tracks papers authored by students and supervised by lecturers, including journal details and indexing status. The conference entity record conference attended by students, including the location, date, and paper presented. Administrative matters are handled by the student fee entity, which tracks all fee transactions per student per semester, including payment status and method. So this ERD provides a comprehensive interconnected structure that support academic administration, research tracking, assessment, and financial management, forming the backbone of our postgraduate data system. This slide provides an overview of the implementation of our postgraduate academic information management system. First, let's look at the system description. The system is designed to simulate a real-world academic environment. It manages various types of information such as student and lecturer record, research project publication, course enrollments, examination, thesis submission, and fee tracking. Essentially, it brings together all the key academic data in one structured and connected system. Now, regarding the development tool, we built the system using the R programming language, and for the user interface, we use the Shiny framework instead of connecting to an actual database. We use it SV file to hold the data, which are read into memory and handled as if they were part of a relational database. This system is based on the entity relationship diagram or ARD that we designed earlier. That conceptual model guide the structure and logic of the simulation and ensure that our entities and relationships align with real-world requirements. A key feature of this implementation is even though we're not using a traditional database backend, the system still behaves like a rational database thanks to how we structure the data and build the Shiny app. This makes it an excellent tool for academic purpose, demos a prototype, and it is lightweight, portable, and easy to use. This slide explains why we choose R Shiny and its supporting tools for this project. First, alignment with project needs. One of the key requirements was to create an interactive demonstration of the data model and its entities. R Shiny is ideal for this because it supports a clean, interactive display that also easy to capture for screenshots, perfect for documentation and presentation purpose. Next, visualization and interactivity. We use Diagrammer R to create customizable and interactive diagrams, allowing users to explore relationships visually. For the tabular data, we use the DT package, which provides searchable and sortable tables, making it easier to understand and navigate entity data. Next, accessibility and reproducibility. All the tools used are open source and cross-platform, which means they are accessible to everyone, including evaluators and developers. Shiny apps can be run locally or deployed online, so the entire system is easy to share, test, and reproduce. Finally, professional look and extensibility. The interface design followed the style of professional data modeling tools, giving it a polished and intuitive feel. And since Shiny is highly flexible, we can easily expand the system later, whether that means adding new. On this slide, I walk you through the user interface and server logic that powers our Shiny application. First, the UI code, which is shown on the top left of the slide. This part of the code defines the user interface for the Shiny app. We use FlipPage to set up the layout, and inside that sidebar layout is used to separate the input and output panels. The select input function provides a drop-down menu that allows the user to choose which entity table to view, such as student, course, or research project. Once a table is selected, it is rendered using DT output in the main panel. Next, the server code, which is shown below. This block defines how the app reacts to user input. The server function dynamically generates or loads the data using generate sample data for each entity type. When the user selects a table from the drop-down, render detail and data table are used to display it interactively in the main panel. The use of reactive values ensure that the data is stored in memory and can be accessed or updated without reloading the app. In summary, together the UI and server code allow for a dynamic and responsive interface where users can explore entity data table in a simple and user-friendly way, which is essential for simulating how an academic database system works.
We define a list of entities that the system will handle. These include tables like student, lecturer, program, course enrollment, research project, thesis submission, publication, conference, exam, and student fee. This section defines the list of available entity tables and runs the Shiny app using Shiny app. It reflects the structure of the system and how the app is launched. Preview of postgraduate
postgraduate.data.csv, we can see a preview of the combined postgraduate data.csv file. This file acts as the main data source for the Shiny application, simulates a back-end relational database using a lightweight CSV format, and it contains record from multiple postgraduate related entities. This is the preview of app in browser. On the left hand side we have student table interface, and on the right hand side we have a lecture table and program table interface. This screenshot shows the working interface of the Shiny app. It allows dynamic viewing of any entity table selected by the user. This view displays the entity table using Git in Shiny, allowing users to sort, filter, and view detailed records. Purpose and benefits. The purpose of this postgraduate academic database system is to facilitate academic administration, progress tracking, and compliance. It also to build a reproducible and flexible postgraduate data model using R and Shiny. And the benefits is to reduce data duplication, ensures referential integrity between entities, integrates seamlessly with data analysis tools in R, supports reproducible workflows, enables interactive reporting via Shiny interface, and useful for academic research and educational use. As a conclusion, this postgrad academic database system offers a structured and a scalable solution designed based on Haberman's data modeling principles. It promotes clarity, adaptability, and stakeholder communication. It also integrates key academic entities such as students, programs, courses, research, assessments, and so on. It also practical and future-ready implementation developed using R and Shiny with CSV-based simulation. It has interactive and insight-driven, which combines data visualization and user interactivity. It lays the groundwork for academic analytics and institutional performance evaluation. Overall, the system successfully bridges robust modeling, practical execution, and analytic functionality, serving as a powerful prototype for modern academic database solution. That's all. Thank you.